Hi, in this video I'm going to go over some hints for WebAssign 6.3. So here we go, let's get started. For number one, we have a spring that's pressed, or a block that's pressed on a spring, and let's just quickly first draw. It's on a table, and the table is 0.75 meters tall. So let's just quickly draw kind of a picture of what this looks like. So we got our table here. There's a spring which is pushed up against a block, and then there's another block that's right next to the edge of the table. Let's just call this block A and block B for the purposes of talking about it. And so basically block A, the spring is going to release block A is going to go along, hit block B, then block B is going to go down and hit the ground. So let's see here. So it's a couple of hints. So first up, what is the potential energy stored in the spring? I mean, it's elastic energy, so it's just 1/2 kx squared. Pretty straightforward. You know what? Just make sure that that's really in meters, not centimeters when you put it in. Here's your k. So let's see here. What is the momentum of the block just before it hits the thing? Well, basically, you just need to figure out the velocity. So just set your spring energy equal to your kinetic energy, and then solve for V, and then plug that into P is equal to mv. So, it starts out with elastic energy. That elastic energy is turned into kinetic energy of the block, block 1, block A, and then you could then solve for the velocity of that, then take that velocity and plug it into P is equal to mv. What is the final velocity of the second block after the collision? So for that, you're just going to basically do the momentum of the block before. So you have momentum of the block ma times by VA before the collision, right? Block B is not moving, so that's going to be plus 0 is equal to MAVA after the collision, after 4, plus MBVB, right? So again, only before the collision, only A is moving, and you're going to have to get, you calculated the VA in part B, right? In order to get B, you would have had to calculate this value right here. And then let's see here, it gives you VA after the collision. It tells you that its velocity is 0.585, and then so that's going to allow you to calculate VB, which is what you're trying to do there. The second block reaches the end of the table. What is its kinetic energy? I mean, that's just kinetic energy is just 1/2 mv squared, and you just calculated the velocity in the last one, right, in part C. So then it falls off from the table. How far does it land? This is your typical, use John to find time. Use x equals vxt to find distance, right? So remember that when you use the John equation, you're going to be doing just the vertical. So you just say y naught is equal to 0, y is equal to 0.75 meters. You know that your acceleration is 9.8. And so that'll allow you to find the time. Again, it's right. Remember that the initial velocity v naught is equal to 0 meters per second. Oh, shoot, sorry about that. 0 meters per second, and so that'll allow you to find it as it goes down. I do not use initial velocity that you found in C, because that's the horizontal velocity. But then Vx, that is right? That is that velocity because it's got a horizontal velocity there. What is its kinetic energy just before it hits? So take your answer to D and add the gravitational energy of the second block, and that's going to equal the kinetic energy after, right? So the kinetic energy of just take the kinetic energy before the ball or the B leaves the table, add in the gravitational energy of B, which would just be mgh of block B, and set that equal to k after. And don't plug in 1/2 kx or 1/2 mv squared for this because that's what you're solving for, right? So just leave it as k after and solve for that basically. So boy on roller blade throws a jug of water away from himself, giving it velocity of negative, so that means he threw it to the left. The boy's mass is 40 kilograms, the mass of the water. So this is your typical rifle problem basically. The momentum before is 0 because again before he threw it. So then you have m of the water, velocity of the jug, I'll use a J for jug, plus the moment m of the boy, velocity of the boy. So pretty straightforward setup. If you need more assistance on that one, go look at the momentum sides, go look at how we do the rifle problem, and do basically the same thing there. Let's see here. For number 3, we have, let's see here, make sure that this is in grams, so that's 0.85 kilograms. So just make sure you've changed that. So let's see here. This is a momentum problem. So basically, right, our change in momentum is equal to is equal to the impulse, which is equal to force times by time. So right, your final momentum is 0, and your initial momentum would be mv, right? Is equal to F times by T. Because it has the word magnitude here, that tells you can ignore the negative because you will get a negative sign, right? I mean, it's going to have a negative sign because of that right there. So because of the negative momentum there, you're going to get negative force. That's because your force is going to be in the opposite direction that it was moving. It was moving 8 meters, positive 8 meters per second. So therefore, right, you're going to end up with a force that's negative. That's fine. So basically, then repeat this. Just use that as your force. Solve for t. You're going to have the same delta p as above as part A. So, right, because basically the emu egg is going to undergo the same change in momentum because it's still going to go from 8 meters per second to 0 meters per second, but now that force just has to be different. So, anyway, this one's pretty much pretty set up. It's again a momentum before equals momentum after, right? So pretty straightforward on that one. You got your two objects, m1 v1 before equals m2 v2 before equals m2 or m1 v1 v1 plus m2 v2 afterwards, right? Don't forget to put in the negative signs. That should be easy to remember because they're given there, but there you go. I would expect, right, it does appear that it's moving to the left. I would expect this to be a negative number. So I think that WebAssign is expecting that. It doesn't say the word magnitude there, so I would think make sure that you're inputting a negative number if it turns out to be negative. So I don't actually know what the answers are at the moment, but let's see here. This one this one is very much like number 3. So wait, hang on. sorry, it's a lot like number 2. So, right, the kid in the jug one. So I'm not gonna spend a ton of time going through that. Yeah. Again, initial momentum is 0. You got the momentum m of the tank, velocity of the tank plus um, mass of the astronaut, velocity of the astronaut. I will say this though, that if right, he's giving it the tank a velocity of a positive momentum, I'm gonna expect this to be a negative number, simply because right, if he's throwing the tank in the positive direction, then he's probably going in the negative direction. So make sure you include that negative sign. And it did ask for the velocity, not the magnitude of velocity. So it's going to want that sign included into that. So okay, number 6 is a very tricky problem. I'll let you read that, but I'm going to go ahead and I wrote up a bunch of hints for us. So I'm going to scroll down a little bit here and let's take a look at number 6. Um, so basically, right, we got this window, which is right in here. You're not given a whole lot of information. So here's the steps that I would go through, and I'm just going to talk through it real quick. So when I set this up, I said we got our initial velocity, which is the top of the building, and I'm going to set right. I'm going to assume it's dropped, so that would give it an initial velocity of 0, and then I just numbered them. I got velocity of 1, which is the top of the window, and I called it y1, which would be the top of the window. I got V2, um, which would be the bottom of the window, and Y2, which would be the height of the bottom of the window, and then V3, which is at the bottom, and Y3, which is at the bottom. And the difference between Y1 and Y2 is 1.2 meters. So let's see, taking a look at the hints that I gave you here, I said step 1, start where you know the most information. So what we really want to do is be able to figure out what V1 is. And to do that, what I did was temporarily set Y1 equal to 0, because it doesn't really matter what it is. So it could just be 0. What I'm really just looking for is the difference between Y1 and Y2. So, because basically what I do know is that um, Y2 minus Y1, shoot, that Y2 minus Y1 is equal to 1.2 meters. Like that's what I know. And so I could just have moved this over there and that would have been fine. Same, it's basically, so if you're upset about this 0 thing, then just do it that way. But anyway, basically what I got is, so Y1 would be, or V1 would become my initial velocity. Obviously my acceleration is 9.8 meters per second. And we could go with, it'll be positive because it's only going downwards. So I'm just thinking of the downward motion of it at the moment. And then I know that the time is 0.125 seconds. So, right, I could obviously solve this for V1, right? That's going to allow me to find V1. So next one, find the difference between Y1 and Y0, basically allowing me to find the height of that section right there. And so I can use the Ringo equation for that. I know that the initial velocity is 0. I know that I already solved for V1 above. And basically, I'm looking for the delta Y, which would be Y1 minus Y0. And so solve for that, basically. So that's going to allow me to get, again, that distance right there. I already have this distance. So as you can kind of see, the only thing I need to do left is find that distance, right between Y2 and Y3. So step 3 is find the difference between Y1 and Y3. Now here's the reason that I did that, because I don't want to have to find V2 if I don't need to. So what I'm going to do is basically, because I know the time for that whole thing is t is equal to 1.125 seconds. And again, the reason that I know that is, so it takes 2 seconds from here all the way down and then back up again. So that means it takes 1 second to go from here all the way to the ground, right? Because it's 2 seconds to go down and back up. So that means 1 second to just go down. So that means, and then from here to here, from 1 to 2, basically, that takes 0.125 seconds. So the whole thing to go from way up here all the way down only, takes 1.125 seconds. So So I know the time is 1.125 seconds. I know the initial velocity is v1, which I found in step one. I don't know what y3 is, and I'm going to just go ahead and set y1 equal to 0 again. Same reasoning as step one. I could just basically say that I could also just basically rewrite this equation as delta y is equal to t plus 1 half at squared. Again, right, our acceleration is positive 9.8 meters per second squared. We know our time, and so again, now we could just solve for delta y or y3, however you want to look at it. And then once you do that, you can now add all the distances together. Basically, you really only two distances if you do it this way, because you're going to have this, the top distance, and then you'll have the second distance, from the top of the window down to the full ground. You really only have two distances you're adding together. That'll give you the total height. So hopefully that makes sense. But it is a very difficult problem. So if you're going to skip one, that's probably a fairly good one to skip. So last problem here. Let's see here. It takes you 0.014 seconds to initially touch and catch a 0.9 kilogram ball traveling at 13 meters per second. So let's see here. We know our initial velocity is 13 meters per second. Our final velocity would be 0, right? Because it's catching it. And we know our delta t is 0.014. So first question asks for change in momentum. I mean, change in momentum, again, you can either find change in momentum by doing F by t, or you can find change in momentum by doing mv final minus mv initial. We'll do that. So, obviously you know what the momentum is, you know what the velocities are, so you could find delta p. It asks for the change in momentum. I'm assuming that this is going to be negative. Because if I plug in a 13 meters per second here, and I plug in a 0 meters per second right there, then I'm going to end up with a negative number. So I'm assuming that's negative. What is the impulse? Well, keep in mind that change in momentum and impulse are the same thing. So you're going to get the same answer for both, um, because impulse is just change in momentum. So now that you know what the change in momentum is, right, you can take that answer, you can plug it into the other equation, and you can solve for F. So um, there you go, solve for F. That's it. So I hope you find this video useful. As always, send me an email or let me know if you have any questions, but I hope you find this helpful. Thank you for watching.